All right, now we are going to discuss the discharging circuit. So we have a capacitor, it has been charged. All right, the capacitor is in here. It has been charged with some charge Q0. So that's the initial charge. And what I would like to do is to connect these two plates with a wire and see, make sure that it is discharged over that wire. But the wire contains a resistor, so therefore this is not going to happen immediately. It's going to happen over a certain time r, and a time constant would also appear in this phenomenon. All right, so the problem is described like that. It's the switch is closed at time t equals 0. Find the charge on the capacitor and the current in the loop at time t. Okay, so as a result, let's just choose our variables. So, of course, the charge on this plate has been chosen as Q0. So therefore, I'm going to use Q as the charge on that particular plate. So let me just color this with white. So Q is the charge on this plate. So that's my variable. And our initial value of that variable is equal to that given quantity Q0. And then I know that, if this Q0 is positive, the current will be positive in that direction. So therefore, I choose this direction for the current. Right? So that's the current variable. I'm going to redraw this thing again. But just keep in mind that my choice for the plate to represent the charge and my choice for the direction of the current, direction to measure the current, they are independent. I just choose them independently. And so as a result, I have to reconcile these two choices. So I have to make sure that the relationship between the variables somehow is expressed in a way consistent with my choices in here. So as a result, let me draw this picture again. So this is my picture in here. So the charges in here is Q. Charge is on that plate is Q, and my current along that direction is I. So I'm expecting that when Q0 is positive, the current is also positive at all times with this choice. So that's why I have chosen. So in that case, you can see that the current is leaving the upper plate. So that's the charge in here. So therefore, minus I is the current that feeds that plate. So therefore, minus I is equal to the rate of change of that that charge. So as a result, our first relationship is minus dq over dt. Okay. Again, let's remember that the sign in front depends on how I choose the direction to measure the current and which plate I choose for representing the charge. Just keep this in mind. So depending on that choice, this sign can be positive or negative. That's one of the things that you have to be careful. The second thing is the loop rule. Let me write this thing down. So this is the point A, and that's the point B. Point B is the same as these points in here. So let me just call them as B because they are just connected with a wire. There's no reason that why I should this in the shape of a square. They are just connected, right? So I need to compute the potential difference between A and B. I can compute this potential difference by going over the capacitor or going over the resistor. So if I go over the capacitor, I know that this is equal to Q over C because this is how we express the charge versus potential difference expression on a capacitor. If I go over a resistor, then this is going to be, when I move from A to B, I'm moving in the direction of the current, all right? It's that direction, it's the direction of the current. So therefore, when the current is positive, potential really drops. So therefore, this is equal to I times R. So therefore, this is the second second equation, IR is equal to Q times C. Just as in the previous case, we just combine these two equations. So I basically eliminate the current variable. So in that case, we get minus R times dQ over dt is equal to Q over C. All right, that's actually even simpler equation. So let's pass to the second page. So we have an equation like dQ over dt is equal to minus 1 over RC times Q. All right, that's the usual exponential function differential equation. We have a function whose derivative is a constant times the function itself. So therefore, it has a solution. Q is equal to some arbitrary constant times e to the given constant times the t. So therefore, we have t divided by RC in here. All right. So, and then I place the initial conditions. So let me also write this thing down. Initial conditions. Right. The initial condition says that at time t equals 0, charge is equal to Q0. So that means this equation then Q0 is equal to A times exponential of 0. So therefore, from here we find A to be equal to Q0. So therefore, charge is equal to Q0 times e to the minus t over RC. Right, that's our solution. And then we have the current, right? Current was equal to minus dq over dt. There was a minus sign. So therefore, together with that minus sign, if I take the derivative, I get Q0 over RC e to the minus t over RC. So as a result, just as we have expected, this is positive whenever Q0 is positive. Let's plot them and see if everything is reasonable. So this is charge versus time. So charge starts from Q0 and then goes to 0 with an exponential decay. And similarly for the current. At the initial moment, the current is non-zero. It has a value of Q0 over RC. And this goes to 0. Again, let's discuss the physics. So this is our circuit. So that's the capacitor and that's the resistor. So let's just discuss first what happens at t equals infinity. At t equals infinity, the capacitor is empty. Right? So the charge on it is 0. And so, well, at infinity, nothing changes. So therefore, the rate of change of the charge is also equal to 0, which implies that the current is equal to 0. So you can easily understand what is at infinity. So again, I'm going to choose the infinity at a finite place. Let's say it like that. So the charge is infinity. Charge is 0 at infinity. Current is also 0 at infinity. So that's what we expected. So everything goes to 0 at infinity. So let me erase this, everything in here. Let me change this to 0. What happens at time t equals 0? So in that case, charge is 0. Charge is Q0. I'm sorry, that's given. That's given. What about the current? So since there's a charge in here, Q0, there's a potential difference between these 2 points, which means that there's a potential drop on the resistor. So let me just call this as VR. Potential drop on the resistor is equal to Q0 over C, right, at t equals 0. Because whatever the potential difference on the capacitor is, there's the same potential difference on the resistor. So therefore, if there's a potential difference on the resistor, then therefore the current should be, the current on it is potential difference divided by R. So therefore, that justifies this value. So therefore, at t equals 0, the current has this value, which is proportional to the initial charge, and the charge has the value Q0. So everything seems to be reasonable. So this gives us an idea, actually, about solving some complicated circuits. So I'm just going to do it like that usually. Let me just draw some complicated RC circuit in here. Let's say that I have only one capacitor. This doesn't work for the case where there are two capacitors, right? So let's say that I would like to compute the current at that branch, right? The current at that branch as a function of time. So usually what happens is that this expression is a constant expression plus another constant multiplied with e to the minus t over tau. Tau is the time constant, right? You need to find this time constant, of course, in this complicated circuit, but it's usually the capacitance multiplied with the equivalent resistance that the capacitance sees, essentially. You can think of it like that. So this can be computed, and this function can also be computed, provided that you can find what these constants are. But by doing the analysis that in the way that we have done, you can easily find these, because you can easily see that, right? At t equals infinity, you know how the current should behave. So as a result, you have some kind of an idea about what the current should be. So in the discharging circuit case, the current would be 0 at t equals infinity. So that's going to be a constant in here. So whatever, by using the physics, you can find this. And at t equals, let me erase right again. At t equals 0, you can also discuss the physics and then find a value for that current, just as we have done for the discharging circuit too. It is some value, let's say. So as a result, you then determine both of these constants that should appear in this equation in terms of these. So you can easily see that, for example, at t equals infinity, this is 0. The exponential term is 0. It just goes away. So you're just left with this one. So that's the DC value in a way. So this constant should be equal to A. And this second constant should be B minus A then. Only in that case, when you replace the exponential with 1, you get the current to be equal to B, right? So as a result, without solving any differential equations, it is also possible to find the time dependence of any property of the circuit.